Hello and a warm welcome from me as well. My name is Master Thesis, and first I want to give the short introduction, afterwards the mathematical background with 3D transformation. Then I will continue with the image registration, afterwards the visual EKF SLAM, what is actually the main chapter because we're putting all information together to build the system. And then I will continue with the results and finally the conclusion. First of all, the problem statement. The accessibility of the subaquatic world is important for research and industry. So mainly this is done by ROVs, so by remotely operated vehicles. But the problem is, at the other end of the cable is always someone sitting to control this robot. And this has some disadvantages. We try to overcome this disadvantage with AOVs, so with autonomous underwater vehicles, because they're first of all untethered, independent, and self-powered. But the question is, if a robot is moving on its own, so autonomously, how to perform the localization of the AOV? Or more precise, the mission success is dependent of the precise localization. So, the vehicle's localization. First of all, it's expressed as a pose, the position and the orientation, which has 6 degrees of freedom in this case, 3 for the translation, X, Y, Z, and 3 for the rotation, roll, pitch, and yaw. If we move on with our robot, so we start here with a certain pose, continuing the next pose, and so on, we are collecting all the data and putting them into a state vector. With this state vector, we are able to estimate the trajectory, as shown with the red arrow here. There are several possibilities to get this trajectory. For example, using inertial sensors, odometry, or to do some kind of sensor fusion, so put different kind of sensors together and get the information from this. But this is in the nature of sensors, they are all prone to drift. What is indicated with these blue ellipsoids. So after some time, the sensor or the error of the sensor is accumulating and the state gets inaccurate. I'm choosing visual odometry in my thesis because of the cameras. They have a much higher spatial and temporal resolution. This means we get more environmental data. But on the other side, the cameras, in comparison to acoustic sensors, they are dependent on light and visibility. So, visual odometry, in short. We have a picture here. Look at the mountain. It's placed on the right side of the picture. The next image, so the consecutive image, the mountain is on the left part of the image. So this means we have a displacement in X direction of the camera. And the visual odometry gives us such information, including for the Y direction, Z direction, and also roll, pitch, and yaw. But this is only an estimation, and this is prone to drift, as I told you, with these blue ellipsoids. SLAM is one successful approach to overcome this problem, because SLAM is computing poses and redefining these poses from time to time by searching so-called landmarks. I do SLAM with the extended Kalman filtering. So, the next step, extended Kalman filtering, in a nutshell, consists of 3 stages. The prediction stage gets the information from the visual odometry, what is indicated by these arrows here, and tries to augment in the next step, the augmentation stage, this state with this information to come to the next stage. So we are at state augmentation stage, and we are accumulating the uncertainties. So these blue ellipsoids gets bigger. And the third stage, which is the most important stage of the EKF, we are detecting loop closings. So we move on, and after some time, we find the loop closing between xk, so x2. So, for example, we meet an environment we already observed. And we get new, reliable data we can put into our system to update the whole trajectory. Related work is quite scarce to this topic, but it deals mainly by correcting the odometry with image registration, like I do. But the difference is what we are putting to x, so to the capital X, what is our state vector. Most of the literature is putting also the landmarks beside the pose to the state vector, over some time the system will get really slow because our matrices, our information is just too much. So online usage is no longer possible, and this is quite bad for an autonomous moving vehicle. Schatzschneider and OSTs are two examples for this, but with different reasons. Schatzschneider is doing exactly the problem. He's putting poses and landmarks to its state. Over some time, the system will be slow. OSTs, for example, put something like a pose to its state, but he's running the image registration, so the update of the trajectory every iteration. And this makes the system slow, because the image registration is the most computational part of the system. In my study, I want to highlight my key features. First of all, I'm using a stereo camera system to obtain 3D environmental information because our AUV is moving in a three-dimensional world. My state X, or my state vector, consists only of poses. The orientation is represented as a quaternion, what is not common in this kind of field. And I have a full 6 degrees of freedom in transformation. What is different to the approach of Bugera, which he is estimating the depth by another sensor, by a pressure sensor. And also deriving the Jacobian matrices to the 3D transformation. And, of course, after all information we have, I'm running the EKF system to correct our localization. So, now start with the mathematical background. The classical transformation consists mainly of two major operations, the composition and the inversion. So, we are at this point, we get new information from our visual odometry, remember, the displacement, and we want to add this information to our state. And this we are doing with the composition, so we are composing this information to this to get a new absolute state. Also, with the 3D transformation, we have to derive the Jacobian matrices to these two functions. Because the robot transformation is non-linear, this means we cannot directly compute the covariances. So we have to use the Jacobians and to use the Taylor series of the first order to get an approximation. So first of all, the composition can be seen as a function with two areas. The first is dealing with the rotation, the other one is dealing with the translation. And again, an example, if we are here at the state and we get the new measurement of our visual odometry, which is h1 to 2, and we want to know where the robot is now, or want to estimate where the robot is now, we have to run this equation, which is using the composition operator. So, let me start with the rotation. I'm using quaternions, as I told you. They have faster computation because of the lack of the trigonometric functions. And they don't have the problem with the gimbal lock, for example, Euler angles have. But we have to keep attention of the accumulation of orientation if we are dealing with quaternions. Because this is not accumulating quaternions, this is multiplication of quaternions, what we see here. And that's already the estimation of the rotation. Because we are taking the quaternion of our transformation, so what's coming from the visual odometry, multiplied by the quaternion of our pose, and this is our future or our estimation rotation, or our estimation of the orientation. And another fact, we can put the quaternion into a rotation matrix as we see here. And again, without the use of the trigonometric functions. The translation part of our function is not as easy as the rotation. Because first of all, we have to rotate our transformation with respect to our orientation of the state of our current pose, P. And this result we can put to our current state. We come from here with this information, what is here, to get this. The inversion, it inverts in transformation. So, if we go with this transformation from here to there, we want to know, okay, how can we go from here to here? We have to invert this or this transformation. This is done by the inversion operator. And with the use of the composition, we can also compute relative motions from two absolute, relative transformations from two absolute poses. But to this later on more. So the task is to invert this transformation. We get some kind of this information, a translation x, y, z, and a quaternion to express the orientation. We put this into a transformation matrix like seen here. We translate the quaternion to a rotation matrix, as shown 2 slides before, and we just invert this matrix. We are taking the translation part, the inverted translation part, put this to our state, and the rotation part, we are not taking the inverted transformation, the transposed rotation, sorry. We are just inverting the quaternion, which is actually by the usage of the quaternion algebra, multiplying every element except for the scalar by -1. So, the Jacobian matrices. Now we are at the point to come from here with this information in the composition to the next state, and so on and so forth, and back with the inversion. But now we have to model our covariances, what we see here. And this is done with the Jacobian matrices. The covariances are uncertainties with zero mean and random Gaussian noise. And for each transformation, so the composition and the inversion, we have to calculate Jacobian, which is done with respect to all its parameters. For example, here, the composition has 2 parameters because we want to add something to something. So we want to add this information or to compose this information with this information. So this function has 2 parameters, so we get 2 Jacobiances. Plotted is only 1. It's not plotted to be seen currently, it's just to see how big this is. If you're interested on the Jacobian, you have to have a look on my thesis. This Jacobiances have the size of 7 times 7. This is due to that the transformation has 7 variables and parameter as well. So both Jacobiances have the size of 7 times 7. With this information and the Taylor series of the first order, we are able to calculate the estimated covariance, similar to the inversion. The difference is we only have 1 parameter because we want to invert in transformation. This gives us 1 Jacobian, and similarly we are calculating the covariance. So after we discover the mathematical background, I want to continue with the image registration. The image registration is really important to run the EKF system afterwards, because this is providing us loop closings. So, we start with pose 0, we get new information from the visual odometry, composing them, getting the new state, and so on and so forth. And with each state, we are storing also the left image from our stereo image system. So we have a corresponding image to our state. To every state, 1 image. And for example, at the state xk, we detect the loop closing, because this has a certain overlap, this image with this one, as can be easily seen. And then we can run the update stage of the EKF. Without this, we cannot update our whole trajectory. So if you don't find something like this, the whole system will do nothing. We'll just accumulate our visual odometry, and the visual odometry will be as bad as before. Pseudocode. Just in short, we put our stereo images left and right into our algorithm, and all recorded images, IN, which are this, and so on, except for this one, of course. This is one of the stereo images. The output is 3D transformation, which is mapping this image, or the camera of this image, in a 3-dimensional manner onto this, which is giving us this relative displacement. So let's start with the find feature function. This is an important function because we need reliable features. For this I'm using SID because they are scale invariant, they have a high reproducibility, and we can compare features to each other. So what we are doing here is We are putting an image into this function, and the pixels are described, or some of the pixels are described as a feature. And each feature is represented with a 128-dimensional descriptor. So this gives us the possibility to compare features with each other by taking the square differences. What we are doing, for example, by the stereo matching. So we have the stereo image from our stereo image rig. And then we are describing the image, each of them, with features, and then we are comparing each feature with each other. For example, this feature fits with this feature, and so on. But the problem is, some feature descriptors are quite similar, but are not correct, so they are actually not matching. For example, this feature with this one here. The descriptor seems to be quite similar, or to reach the threshold, but it's wrong. These are called outliers, so we have to discard them. And for this, I was using Ramsek. And the result of Ramsek can be seen in this image. All features are perfectly matched. So, we discover the stereo matching and find feature function. So we have now translated our stereo images into feature sets, which are perfectly aligned to each other. This means, first of all, they have the same size, so the same amount of features. And secondly, the first feature of FL fits to the first feature of FR, and so on. Now we have to find from our all recorded images and feature set what is matching to FL, because our system is running also always with respect to the left image. So we are comparing this with the left image and our temporal image now, because we are iterating over all images we already recorded. During this matching, I'm also running Ramsek. This means that, for example, FL will lose some features, and this means that FL and FRs may be no longer aligned to each other. That's why I'm using the update feature function here, because we have to be assured before running these two functions, or especially this one, that FR and FT has the same amount of features, and they are all perfectly aligned to each other. If we do so, we can calculate the 3D points. So we're taking from our stereo image system the translated features, and with respect to the reprojection matrix, we are able to calculate the 3D points from these stereo features. This reprojection matrix is filled with the camera intrinsics. So we are going now from 2D to 3D. So we are multiplying the reprojection matrix times our vector here, what is filled with the left features, xy coordinate of the left feature, and the disparity, what is the disparity between the left image and the right image, x coordinate of the current feature, because we are running this for every feature. So for every feature in our feature set, we are getting now 3D points. And with this, we can run the solve PMP Ramsek. Solve PMP Ramsek solves the perspective endpoint problem by estimating the post transformations, or exactly what we want to do, because we want to map now the 3D points from the stereo image system onto our loop closing candidate features by minimizing the reprojection error between both of them. The result is a 3D transformation with a rotation and a translation. Here's one example. On the left side, we see the left image of our stereo image system. In the middle, we see the potential loop closing candidate. So we have a certain amount of matchings between each other. Now we apply solve PMP Ramsek, and the result can be seen here. Solve PMP Ramsek provides us with a 3D transformation, which is transforming this image onto this image, what can be seen here. All the areas unequal to purple, perfectly matching to each other. The purple areas, they are errors, but in this case they are not really errors, because both images are not showing exactly the same overlap. So for example, if you have a look at this corner, you see the white area maybe 10 centimeters. Here, you see much more of this area. So they are not overlapping exactly to 100%. And if you have some kind of not overlapping areas, the system will tell us as an error. But all the other areas which are overlapping are fitting perfectly fine. So now we can go into detail with EKF SNAP. EKF is first of all a Bayesian filter. State estimation of nonlinear systems by using the normally distributed Gaussian noise. So exactly what we were working for. Again, consists of 3 stages. The pseudocode looks like this: prediction stage, augmentation stage, and then the main effort, the update stage. I will concentrate on this and these 2 stages just in short. Prediction stage. We get the last covariance C. Beside the state vector we are building, to each state we are also storing our covariances, so the uncertainties. This is done with this global matrix C. We are putting the calculated covariances on the diagonal on the bottom right. And to get the last one, or to get the covariance to the current state, which is the last state in our state vector, we just have to take the bottom right 7 times 7 covariance. The composition is done as shown in the 3D transformation. And the augmentation stage. Also, I will explain only at covariance. Again, we are augmenting also the covariance, not just the state vector, because we want to have information about the uncertainty to each state. We are extending C by 7 rows and 7 columns and put the new covariance computed with by the composition, as can be seen here, at the bottom right. Other areas, so E, F, D, and B in this case, so the last column and the last row, except for the element on the diagonal, will be calculated separately. And I want to refer at this point to my thesis. The update stage, it's dependent on the image registration. No update, no image registration, or no successful image registration, no update. It's the main part of the EKF. The key features are the observation function H, the observation matrix capital H, and the innovation Y. So let's go into detail. The observation function H and observation matrix are both calculated in the pseudocode in the function calc HKK. We have now information from the image registration, which is telling us between this image of this state and this image of this state, we have an overlap and an image registration, so a 3D transformation. So now we are going to start to look up the states corresponding to these images, so xk and x2, and we are calculating the relative transformation as seen here. And finally, our inversion of the transformation is used. So first, we are inverting k, so we are going back, and then we are composing this information with x2, and the result is our relative transformation between xk and x2. It can be seen here. And this is our observation function h. If we found multiple loop closings, for example, between xk, x2, and xk and x1, our observation function will grow like this. And with this, we have now comparable results, because we have a relative transformation given by our state vector, and we have a relative transformation given by our image registration, zk. The observation matrix capital H is storing the Jacobian matrices, and it's built like this. First of all, it has as many rows as loop closings times 7, and as many columns as states we are storing in our state vector, because we're building the partial derivatives of H with respect to our augmented state. This means if we are building them, in this case, the loop closing or the states used for all loop closings is only xk and x2. This means only the third position and the last position will have terms unequal to 0. For example, I put here another loop closing with the fourth position and the current state. Innovation. In the sense of EKF, it should be big if Z and H are different. This is true for the translation. We can just subtract them to get the innovation for the translation part between Z and H. But because we are using quaternions, we have to deal with some special kind of treatment. Different quaternions can express similar orientation, as can be seen here. The quaternions are quite different, these two. The first quaternion is given by Z, the last one is given by H, but they express more or less a similar orientation. and if we subtract them just, we will get a big innovation. In the sense of a quaternion, this is a really big number. So what I was doing was building the absolute values and subtracting them. This will give us a small innovation, in this case, what is actually true. Pseudocode again. We went now through all the stages up to here, and now we can just apply the standard EKF standard equations, K, to calculate Kalman gain, update our state vector, and update our covariance measures by applying the standard equations. So we'll skip this here. And finally, we have to add the stereo images, or the net stereo image, to our recorded image set. The results, I was using this laptop with Ubuntu 12 and running MATLAB 2013, and the implementation was using only a single core. The mission was recorded with ROS, with this AUV, and the advantage of ROS is that we have this ROS-back function, which is providing us an offline playback. So we recorded once the mission, and we could playback this mission as often as we wanted in our laboratory on our laptops, without going to the water tank where the mission was recorded inside the URB. The visual odometry, I was using a library called libvisual2, and the ground truth we were collecting because of the reason we put in a poster inside the water tank so we can easily measure how the robot was moving. So the test was a 23-meter sweeping task with different noise levels, or why different noise levels? Because we want to see how the system will react to highly corrupted or to less corrupted odometry. We are starting with a noise level of 0, or 1, with a covariance of 0. So we are taking the visual odometry as it is, and going up to a noise level of 6, and the visual odometry is more or less not usable with this covariance. And the error definition looks like this. We have difference between the ground truth and the odometry, and the ground truth between EKF slam. And we are dividing each differences by the length of the trajectory, which is 23 meters. And the error units are meters per traveled meters. So, here are the quantitative results. From the noise level of 1, so no corruption of the odometry was away from, or in mean, away from the trajectory of 38 centimeters. EKF was correcting this to 27 centimeters. This is giving us an improvement of 28%. With a highly corrupted visual odometry, we have an improvement of 86%. This is typical for EKF, because if you're feeding a good running EKF system with less accurate data, the error of EKF is only slightly increasing. The quantitative results, we were using some kind of image or frame separation, because as I told you, OSTs was running the image registration as every iteration. For example, with a separation of 2 frames, so run the image registration every second frame we are getting from the stereo camera rig, I had an error of 28 centimeters and runtime of 8 minutes 4. But with a separation of 4, I was already faster than the mission time. So an online usage is possible. The qualitative results. We see here in blue the ground truth, in black the visual odometry, which is far away from the ground truth, and in black the corrected black one as taken by the EKF slam. The magenta lines are loop closings. This is the result with a noise level of 4. The odometry is going far away from the ground truth, and EKF slam is still close to the ground truth. And even worse for the odometry, and still good with an EKF slam. I want to show you a video with a separation of 2, noise level of 3, and the playback 4 times. Again, blue the ground truth, black is the odometry, and red is the EKF slam. Right now, EKF slam and odometry both is perfectly aligned because we don't have any update right now, so no loop closing was found. And at this point, we found the loop closing between this state, and it's correcting. And now they're going different ways. So you see the odometry goes far away, and we will find the loop closing in several seconds again. Here. So, look at this point. Here is right now the EKF slam estimation. After the update, it switched to here. And if we find more loop closings, we will EKF slam will correct this even more. So, for example, I've found here something around 7 loop closings. EKF slam. Okay. And here, perfect. It's near to the end of the ground truth, but the real odometry is far away. My conclusion. I was proposing a post-based visual EKF slam approach by the usage of only stereo camera data, no other sensors. And using pure 6 degrees of freedom, the orientation is represented as quaternion. Again, this is not common, and the improvement was, for example, with a noise level of 6, 86%. And with a separation of 4, which still provided us good results, the execution time was under the mission time, what is important for autonomous underwater vehicles. And my future work is fine-tuning the measurement of and observation covariance matrices to get even better results, further tests in the sea, and the ROS implementation to provide this approach to the whole scientific world. Thank you very much, and here's the literature as told in the section of the related work.